Thanks for sticking around this long. I know the snows out there is beautiful. I'm Rob Annand. I'm a senior security AI/ML engineer at Adobe. I know that is a very long title. Titles are getting ridiculous these days. And I'm excited to talk to you all about RAGs. Before I get started, quick show of hands, who in this room has built a RAG before or worked with RAGs in any capacity? Awesome.
Wash windows. Honestly, I've never heard of one.
Yeah, I'm going to be talking about ShamWow, for all so a little bit about me. I have a very unconventional career and didn't really follow a traditional career path, and which has led me to a lot of interesting industries and worked on a ton of cool problems, and it has eventually led me to Adobe. So I actually started off as a race car mechanic for a private Porsche race team. I didn't know what to do with myself when I was 18. And then I got fired, and I was told I was too smart for that, needed to go back to school, so I did. Then ended up at DHS working as a cybersecurity analyst in the early days of US CERT, almost overlapped with Bryce. And then I pursued a path in data science when all this started becoming big in around 2012-ish, time frame. So I've been in this industry for about 10 years now. I'm really passionate about building end-to-end AI and ML solutions. Education, open source. I'm currently working on a LlamaIndex contribution. A lot of that has stemmed from the work here. And just to kind of show some of the crazy things that I've done, this is a $250,000 military-grade camera working on an end-to-end machine vision system project for the military. This is me on a roof in DC. I'm from Virginia, so if there's any DMV people, would love to connect afterwards. So my theory, or my theme for this is hacking and unconventional approaches to problems. And so that's how we got to RAGs and cyber operations. So before I dive in, I'll talk a little bit more about the average day of an analyst at Adobe, give a quick intro to RAGs, give a little bit of a tech overview, talk about how we can do some search enhancements, some generation enhancements, and then wrap it up, and then also talk about our current app that we recently deployed called Tribore. Any Final Space fans in the crowd, that's where that name came from. So a little bit about the day in the life of an analyst. I pulled these stats last week, so they might be a little off, but typically an analyst will triage about 8 to 10 detections a day. This is not including any automation or low severity things. And from looking at our time to close, the average time can range from 15 minutes to 2 hours. This can also take days. So some of these are longer, shorter. And what I noticed, I spent a lot of time working with the detection engineering team at Adobe and also working with our operational analysts just to kind of see what are the hard things that they're facing day to day. And what I noticed was that they spend a lot of time searching and collecting data. And so can we build an AI-powered cybersecurity search assistant? So just to kind of give you a little context into the problems that we're facing at Adobe, we have over 10 petabytes of security logs. So that's a lot of logs to sift through, right? SQL queries, correlation searches, you name it. It's not easy. And traditional search, just search in general is hard. Whether that's exact search or you're trying to do wildcard, SQL, you name it, it's time consuming, it hurts your head. I don't advise doing it that much. And so we need to be able to provide analysts with near real-time intelligence search. And so that's what we're leveraging RAGs to do. So the simplest RAG, this is simply hey, let me just take all security data, throw it into an LLM, let the LLM do the search for you, and then generate a nice little report. So there are some problems with this. There's no retrieval part of it, so we're not giving it, we're giving a lot of irrelevant information. There's no chances to do enrichment, and it might misinterpret the logs based off of what your prompt is. So it can generate misleading conclusions. So what we can do is we can take our security logs, we can then upload them into a vector database, so that way when a new log is passed, it can compare that log to logs that we've indexed to find similar logs, pass that to an LLM, and then generate a more, better detailed log analysis report that's more relevant to what the analyst was originally searching for. So I was told I'm not allowed to share Adobe cybersecurity log data here, so I did find a cool proxy for this that I use for some of the examples. There's an open source repository called NL2Bash. So if you're interested in working with process command line strings and NLP, this is a great data set to kind of get started with. And so what I'm going to do throughout this presentation is kind of share some of the advanced techniques that we've tried and apply it to this data set to just kind of show how it works. And so it's a very simple data set, but you get a CLI string and then you get a description. And a lot of these are hand annotated. They come from Stack Overflow and from other sources. So at Adobe, we use Databricks, and so we're using Databricks vector search. Now, there are a ton of vector databases out there. I'm not here to talk about pros and cons of the different vector databases. All of our security log data is now being stored in Databricks, so it makes it very convenient for us to use Databricks vector search. And so it allows us to just take a user query, and then it will respond with the top similar process commands. So this is one of the NL2 bash commands. So how does this all work? And so the project is named after Tribore. He's an alien from the Final Space comedy show. So vector databases, and this is a lot darker than what I hoped it to be, is, kind of think of it as a large knowledge base, or in this case, like a library. And we are storing these logs in a dense vector representation, and so those vectors that are close together are going to be, here they're going to be very close together. And so then that way, when you have a new query that comes in, then you can compare that and find vectors that are close to one another with math like cosine similarity. So in order to do this, machines just don't understand raw text, so we need to convert it in some way. And so at first, we use tokenization, and so why this matters, it splits up the command into manageable pieces that can be mapped to a vocabulary, and then can later be embeddings can be created by. And so this is what the machines use, and this is also what the models can interpret. So here's kind of the diagram of how that works with. That did not wrap correctly. Sorry about that. But we can take one of these process commands up top, and then we can generate the tokens, and then we map it to a known vocabulary or trained vocabulary, and then we can generate the dense vector embeddings. And this is what gets stored in the vector database and what we do our comparisons with. A little bit about understanding vector search. So how is it different than keyword search? It's almost like you're trying to find a word in a book. So as you can see here on the left, this poor person is trying to flip through every single page and find that exact word, where vector search allows us to find patterns that even when exact matches do not exist. And so this is very important in cybersecurity because a lot of times when you're working with different process commands, or executables, they're going to have different file paths, they're going to have different software versions. Adobe is very large. We have lots of business units, users, contractors, and so vector search ends up being very helpful here. This is one of my favorite examples to kind of show how this works. So you have a query of thrash rock, and I want to find all bands that are considered thrash rock, like so Anthrax, Metallica, and Slayer, and naturally they are going to be very far away from Bob Dylan, or one would hope. Indeed. So in short, this is the vector search pipeline. So we're going to take all of the security logs, run them through an embedding model, store those embeddings in Databricks vector search. And then when a user has a new process command or security log that they're interested in searching, they can then run that through the same embedding model, which will then compare that with the other embeddings that we've stored, and then generate them a list of results. So like the top similar commands or security logs, depending on what you're indexing. So how can we make it better? Ha, ha, ha. Any Tim the Toolman fans out there? So we need more power. A simple RAG is not enough. We need to add 50 more horsepower at least. So one of the things that we can start with is just better indexing. So we can look at how are we chunking the text. We can then also work with specialized embedding models. So we can use domain-specific models to capture those nuances. So with like cybersecurity or just logs and code, which I'll talk a little bit more later, we can see how those models improve how we can index this data. Then another thing is metadata enhanced indexing. So besides just the process command or the log, we can also take additional attribute data, store that with the vector embedding, and so that way when somebody runs a query, we can even pass that information to an LLM for enrichment, or it will give them more context around what it is that they're searching. So chunking text, this is really just dividing the text into manageable pieces. And so this is a very simple example for a process command. This is overkill. We would not, with today's models, we don't need to have a chunk size of 25. But then, typically what happens is you also need to have some overlap, because when you retrieve these chunks in the vector database, it's not going to be retrieved all at once. And so sometimes having some of the before and after can help the LLM during the generation part. And what we've found to work the best for us so far with the process commands and security logs that we're working with is a chunk size of about 5,000 with a 20% overlap. And that, so far that is working well. Another project that we are working on is we're ingesting security documentation as well as tool documentation. And what we found is actually converting documents to Markdown and then using special Markdown parsers to extract the information. It will preserve the hierarchy of the document. It won't break up. So if you have a bulleted list, it won't split up on the list. And so we have found this to work really well. And this is not an exhaustive list. There's a ton of different chunking strategies out there. But these are kind of like the two for right now that have just been working for us. Now for a specialized embedding model. So we saw earlier we had a bunch of tokens, and it didn't seem like it was really keeping the structure of the process command. And so what we found actually is that using these specialized code embedding models, the one that we particularly use at Adobe is called jinaai, and it's so far the best model that we've found out there that's open source. And then this will actually preserve the structure of the process command, and it was actually trained on code, Bash, PowerShell, and 38 other programming languages. So it works really well with cybersecurity logs. The next thing that we can do is metadata filtering. And so think of this as like a where statement in SQL. You might want to filter out things before you even run your search. And so that's what this allows us to do. So if we have a process command or a security log with an event date, we can set that filter. And then that way it will run that filter and it will ignore those records and then only search on event dates, in this example, after February 1st. So you can also do this with additional data, and that's where that metadata really comes in handy, is it allows you to build these specialized filters, so that way you're increasing the chances of getting more relevant information. Another thing that you can do is you can actually use machine learning, or one of my favorite things is just writing prompts with LLMs and having them doing entity extraction. So maybe one of the things that we want to do is extract the different commands and flags, and we want to store those as metadata for either filtering or just to kind of help the LLM during the generation part when writing an analysis report. Okay, so after we've kind of worked on improving the how we index the data and add metadata, some of the other things that we can do is improve the retrieval part. One of those is hybrid search, and another one is LLM re-ranking. And there's also many more strategies out there than this. These are just the two that we've tried so far, but we're going to continue as new strategies come out and try and apply them to our domain. So how does hybrid search work? It's kind of like the best of both worlds of vector search and full text search. And so what it's going to do is it's going to run the cosine similarity on those dense vector embeddings that we created earlier for those process commands. And then it's going to create a sparse vector of those process commands and then kind of do keyword search on us. And then we're going to combine those scores together in what's sometimes called as a fusion score. And so then we get a new ranked results. And so this kind of gives you that example. We ran the same. So I generated an in-memory, I created an in-memory vector database, and I ran the same command through a semantic search as well as hybrid search. And so if you look on the far left, we do have some pretty high cosine similarity scores for the grep zombie commands, but then we also have some scores that are closer to, a little above 0.6. And we can have another talk about thresholding and cutoffs. It's a little arbitrary. But then when we run it through hybrid search, now it's not apples to apples comparison, but the one thing that I wanted to point out is that now we have more separation. So those commands that do not have zombie in them have a much lower fusion score compared to those that do have it. So we're able to pick up on those keywords better. And so this is where it kind of helps. And cybersecurity has a lot of specialized keywords, and so or other domains as well, healthcare. That's why we have found hybrid search to work the best for us. LLM re-ranking, honestly, the verdict is still out. We have not found it super helpful, but I figured we would mention it. It might be helpful in your use case. And so what this does is it allows you to kind of cast a wider net. So maybe you still want to retrieve the top 5 similar commands, but maybe you will, with your semantic search, you'll retrieve 10 or even more. And then you use an LLM to then do the pairwise comparison for you and then re-rank those. And so some things that might be, their cosine similarity scores might be lower, but based off of the instructions that you gave the LLM to do the re-ranking, it actually might bring it up. We've been getting a lot of mixed results, so we haven't deployed this strategy yet. We're going to keep iterating on it, but I thought it was worth mentioning at least. So the next step is actually improving the generation part. And so I know prompt engineering is probably not an advanced technique, but I'd share some of how I approach prompt engineering. There's also query rewriting, as well as now LLM fine-tuning. And that is actually getting easier and easier to do each week. And I'll share how we're approaching fine-tuning models at the moment. So prompt engineering. So there's a couple things that we can do. Obviously we need to write a good system message, a good user message. And then another thing that we found, some of these logs are really large, and we're using our own self-hosted foundational models, so we don't have the 2 million context window that Gemini gives us. So we found that adding a refinement prompt helps, and what that does is as you're building the final analysis report, what it will do is it will kind of preserve that information and then take the next chunk and then see, does it need to use that, then add it and keep updating the report incrementally without kind of losing the original thing. Sometimes when I've worked with this without using a refinement prompt, like the log analysis report that I'll show in a sec, it will get chopped off or it will kind of get a little screwed up. So this is kind of how I like to save prompts in YAML files, but I like using Markdown format. And one of the things that I do for prompt engineering is I actually ask the LLM how it prefers to be prompted. I know it sounds silly. I have these kind of therapy sessions with ChatGPT or these other models, and I go, hey, here's the input, here's the output, here's my prompt. How would you like to be prompted? And that seems to work so far. And using these process commands, these are the types of reports that we can get. Now, in our cases, we're actually experimenting with taking all the process commands, and we have more enrichment data, like we have historical risk, we have the severity, we have the historical closure statuses, and then we have the LLM analyze that as well as the analyst closure comments to see if the new process command that they're searching, to see if we have anything, if we've seen this in the past, how was it handled? How was it closed? What were the closure comments, et cetera. The next thing is query writing. And so what you do here is you actually have an LLM rewrite the query for you. We might not always be the best at writing queries, and so we might need a little help on how do we prompt the LLM, or even how do we ask the right questions for the vector database to get the best results back. Another thing that you can do too, which I'll show an example of, that we're starting to explore with, is kind of anticipate. So actually have it generate more queries based off of the original query. So like maybe we're just interested in the parent, in the primary command, then the subcommands, and then run those searches in parallel, and then do a retrieval fusion approach where then we look at the results of all and then combine. So this is something that we just started looking into. The verdict is still out, but this is a pretty neat advanced technique that we're seeing that is showing promise in other fields. We're just trying to see if we can get this to work for us in cyber. So fine-tuning LLMs. So the important thing here is like we're just taking off the shelf. Now, a lot of these foundational models in ChatGPT, they're obviously scraping the webs and they're reading cyber papers, research papers, so they have a good understanding, but it might not have a great understanding of your specific environment. And so you can take models like SecureBERT or take one of these foundational models and then fine-tune it on your own data. And one of the approaches that, or one of the frameworks that we found that works great is called Unsloth. And it's really simple to fine-tune your own model. I was able to actually run this in Google Colab, so you don't even need anything special. This was completely their free tier. But then I was able to take a Llama 3 model, 3 billion parameter, just run it through 60 iterations on this NL2 bash data set. And I was able to fine-tune it and generate a response that looks similar. It's not great, but at least it's in the ballpark of what the annotations that we have in the NL2 bash. Now, as you can see, the training loss is still fluctuating, so it hasn't converged yet. So obviously, we run this longer. Hopefully, it would converge or add more data. So, kind of in summary, these are the different strategies that we've tried so far at Adobe to work with these process commands and security logs to build a vector search. Working with different chunking strategies, embedding models, enhancements, improving the retrieval step, as well as how can we improve the model output from these LLMs. Just to kind of get a little overview, this is what our actual deployment looks like. So we're pulling in our endpoint detection logs as well as notables, and then we're generating the embeddings for those. We also have, we're creating the metadata from that information. We have a couple traditional ML models that are in place that are actually scoring those logs as well, so we can know like how suspicious one of those are. And then we're storing that as metadata, so that way when we do generate the output, the LLM has that information when it does the analysis. So all of that's stored in our Databricks vector search. And then we have a couple API endpoints, so we're using LlamaIndex. Our jinaai model is hosted through Onyx. Most importantly, probably should include in this talk, is that we're also tracking all this information in MLflow. So that way we can see every query. We can see how the LLM was behaving. We can see what was retrieved. And this will allow us to make improvements to our approach as we collect feedback from analysts and end users, or if a bug happens or they get a weird result back, we can then go back and debug our pipeline and see how it all works. And how we've integrated this is like we have a CLI tool, so people can run these searches from the command line. We also, one of my colleagues has built an amazing Chrome extension, and this allows analysts to essentially, without having to open up yet another web app, whatever page that they're looking on, and if there's information that they want to search or run something against, they can highlight that, and then it can run through Tribore, and we can retrieve all those results. All that information gets displayed to them, and we do some comparison analysis as well in there. The next step, once we kind of finish fine-tuning this, once we finish fine-tuning Tribore, our goal is to then completely automate this. And so that way, in our SIEM tool, whenever a new detection happens, it automatically runs the search, collects all the information for the analyst, and then dumps it as an artifact. So that way they can just review the output themselves. And then if they need to do some additional searches, they can as well. That's it. Thank you so much. Any questions? Yes?
What was the embeddings model you said you used again?
So jinaai.
Jina.
Yeah, Jina.
With a G or
A J. Yeah. Yeah, they have quite a few models on Hugging Face, but we use their code embedding model version 2.
What's your ROI cost on this? Are you calculating it right now?
The ROI? So we just deployed this about 3 weeks ago, and so we're getting about 10 hits a day. So it's a new tool that we're trying to get into the analyst workflow, and we're currently about 5 people are using it at the moment, and we're getting about 2 hits per user is what we're kind of averaging at the moment over the last few weeks. Yeah. So.
Now, a follow-up question on that. You said you guys are also using a historical data in the stream. You guys are just bulk uploading it? How is the tool you guys use?
Yeah, so all the historical data, we use Cribble to pull all the historical data into Databricks, and then all of that is saved in Databricks for us. And then we create a special view. We have machine learning models that are then scoring that data that we're pulling into a separate view, and then we use that view to create the index from.
The scoring is defined, or you're using some predefined scoring?
Oh, no, so we built some custom machine learning models to take the process command or the log and tell whether this needs a human review or not. So we're looking at, how suspicious is this log? Based off of, we have thousands of annotated, logs. Yes.
So when you were explaining the hybrid search,
Mm-hmm.
you're talking about like searching the embeddings semantically and then also having a keyword search.
Mm-hmm.
How do you, I get the cosine distance function for like embedding your query and then finding the distance between that and like your database of embeddings, but where do you get the score for the keyword search?
Good question. Yeah, so a separate index is created for sparse vectors, so it essentially just kind of tokenizes it, and then it does the keyword search against that. So yeah, so it's two indices. Any other questions? Yes.
So what kind of a machine learning algorithm are you using? Are you using KNN, something like that?
For which part?
For the search?
Oh, for the search? No, we're just using semantic search or also hybrid search with cosine similarity. We're not using KNN for. Yes.
So is it Cribble that you're using to do a lot of the metadata enrichment? Or how are you, what metadata are you pulling out, and how are you finding it and adding it in there?
Good question. So yeah, where are we getting the metadata from? So that is coming from the annotations that the analysts make in our SIEM tool. And so we're pulling, like computer name, the agent ID, the event date, what was the closure status, the business unit, and other information like that.
Gotcha.
All right, cool. Yes.
So where do you store the information? Are you storing it in the local operation system, or cloud, or edge?
Yeah, cloud. Mhm. All right. Well, thank you very much, everyone, and I hope you have a great weekend.